Imagine you were trying to read an encyclopedia that holds all the information in the world, but instead of a set of books, it's just one single volume. It weighs 10 tons. When you drop it on a desk, the wood splinters and buckles. You couldn't even lift the cover to turn the pages. When a new software application grows from a handful of users to millions, the servers running it face this exact same physical limit. Keeping all that data on one single computer becomes just as impossible as managing that 10-ton book. The machine runs out of memory, the hard drives fill up, and the whole system stops moving. To solve this, we use a technique called partitioning. Instead of building one impossibly huge machine, you break that mountain of data into smaller, manageable chunks. Each of these chunks is sent to its own independent computer. These individual machines work together as a team, with each one responsible for its own small piece of the total library. But now you have a new challenge: finding things. If you have 10 different computers, how do you know which one has the specific information you need? You use a key, which works exactly like the letters printed on the spine of an encyclopedia. You check the spine to see where your word lives, and you go straight to that specific book on the shelf. Moving away from a single machine solves the problem of physical size, but it introduces a whole new puzzle. You have to design a precise set of rules for how to organize your information across the network so you can still find anything instantly. The most intuitive rule is to sort everything in a continuous line. For example, we can tell the system to put every user action from January on the first server, February on the second, and March on the third. Sorting this way makes reading the data incredibly fast. If you need to look back at everything that happened in March, you don't have to search the whole network. You go to that one machine and grab the whole month in one fluid, continuous motion. But there is a massive problem with this perfect line strategy. Think about what happens right now, today, in the present moment when millions of users are actively clicking and posting in real time. If today is in March, then every single new piece of data is being sent to the March server. While the January and February machines sit completely idle, the March server is being bombarded by the entire weight of the app's traffic. It becomes a bottleneck that eventually crashes while the rest of the network does nothing. So while sorting by date makes reading the past effortless, it forces the entire present-day workload onto one machine. The system is physically large enough, but it isn't balanced. To keep the load balanced, we need to scramble the incoming data. We use a mathematical formula that takes a piece of information, like a timestamp, and turns it into a random-looking destination. This formula acts like a dealer at a casino, shuffling the cards so no one knows exactly where the next one will land. Now, the incoming work is spread perfectly across every computer in the network. No matter how many millions of people are using the app at the same time, the entire system stays balanced and stable. But we've traded away our neat chronological order to get this balance. Because the data is scrambled, you can no longer find a specific week of activity by visiting just one machine. The March data isn't in one stack anymore. It's scattered in tiny pieces across the entire network of servers. To find that data, the system has to shout the request to every machine at once. It has to ask every server to check its own local pile, find the March fragments, and then stitch all those scattered pieces back together in the center. Engineers must choose their rule based on the app's priority: read massive chunks of history or handle millions of writes without the system crashing. A year later, your application has doubled in size again. You've run out of room, so you buy a new computer to add to the team. If your data is stored in a few giant solid blocks, moving it is a nightmare. It's like trying to move a 10-ton encyclopedia as one piece. You'd have to shut the whole library down for days just to haul the weight to its new shelf. The secret to growing without stopping is to think small from the very first day. Instead of a few big chunks, you split your data into 1,000 tiny pre-packed boxes. Even if you only have 2 servers to start with, you still pack the data into these 1,000 little boxes. Now, when that new computer joins the team, it doesn't trigger a massive, slow migration. It simply reaches out and takes a handful of those small boxes from the other machines. Because the boxes are small and their contents never change, the keys used to find the data stay the same. The rules don't break just because the boxes move to a new machine. This relocation happens quietly in the background while the application keeps running. users never notice that the data they are looking for just moved to a different machine. This invisible choreography is what allows the internet to scale. By breaking massive problems into tiny, movable pieces, applications can stay fast and stable whether they're serving 10 people